Now we'll consider a property of Laplace transform called time scaling. Let's say I have a function f of t and you know its Laplace transform f bar of s, and you want to know how to find a Laplace transform of a function with a scaled argument a times t, where a is just some positive constant. So let's start by just recalling what is Laplace transform. It's an integral. So you take a function and you integrate it. If you don't remember this, please watch the previous video. And the aim of the game is to find Laplace transform of a function with a scaled argument. By definition, it's just another integral where you put a function of a scaled argument inside this integral. And it's natural to use another variable, let's call it z, to evaluate this integral. So let's look at this in more detail. So you take a substitution, z equals a times t, or you can express t as z over a, and also have a relationship between the differentials. So the integral transforms to this form. Note the difference. It has a factor 1 over a in front of it, and also inside it has an exponential to the power of s over a times z. Also note that the limits are not changed and that there is a new factor s over a. So there are two differences. One is this scaling factor inside the integral, and also a scaling factor in front of the integral. So if you look closely, you probably will realize that this is nothing else, nothing more than a Laplace transform of original function, but with a scaling factor in front of it, and also inside, its argument is scaled as s over a. And that is exactly what is called the time scaling property. So now, if you have a Laplace transform of a function f bar of s, all you do is you just scale it with a factor 1 over a and also replace its argument with s over a. Let's look at an example. So you probably recall that Laplace transform of sine t is 1 over s squared plus 1. If not, please watch the video before. So how to find the Laplace transform of a sine omega t? In this case, omega is just a scaling factor a. So we use this property to put a scaling 1 over omega in front and also inside as s over omega. And if we simplify it, we get an expression which is a Laplace transform of a sine omega t. So that's it. And this is one of the first examples which we'll later see in a table of Laplace transforms. And this is the next part of this video. Laplace transforms by table is a very important concept. It helps you to save time and get your computations quicker and avoid mistakes. It's really cumbersome and inconvenient to keep using definition of Laplace transform. So if possible, always trust to use the table. So pay attention now as I go through the table and look at some of the common functions you might see in the examples and in the problems to solve. So on the left you see the function f of t, and on the right you see a Laplace transform of this function, which is f bar of s. So first is Laplace transform of 1 is just 1 over s. It will be helpful if you can check this as an exercise to convince yourself. Then we have a Laplace transform of a power of a function t to the power of n, which is integer number. let's look at the n equals 1. Then Laplace transform of t is just 1 factorial s 1 plus 1, which is 1 over s squared. And this is exactly what we showed previously, so this is right. And also an exponential will transform to 1 over s minus a. And this is another example we considered previously. And we just shown that sine of omega t becomes that. Similarly, we can look at the cosine of omega t. Note that the difference will be in the numerator on top. Likewise, we can look at the hyperbolic functions like hyperbolic sine. And the main difference here will be the minus at the denominator. Or hyperbolic cosine. Or we can combine two functions. We can multiply t times sine omega t. Or with the cosine. And likewise, we can take an exponential multiplied by the sine and get another expression. And by the way, this is another property called S-shift, which we'll come to later, so don't worry about this for now. But it will produce a minus sign at the denominator. And also you can look at the exponential times cosine. Or you can combine this with the hyperbolic functions. Right? So again, look at the difference between the normal and hyperbolic functions. And also pay attention that you have this factor, then you have an exponential. Just a few more functions, so bear with me. This is a step function or a Heaviside function. I'll talk about this in a moment. And this is so-called impulse function. And this is very interesting. It's actually not really a function, it's a symbol. And let's try to get some feeling to what this function or generalized function is by looking at the hump. So let's say we take a function f of t, which is 1 over 2 pi sigma squared to the power of minus exponent t squared over 2 sigma squared. So if we'll plot it, it will look like a hump, and you might have heard it under the names of Gaussian or normal distribution. And as you reduce the width, as you reduce the sigma, it will become narrower and taller, and yet narrower and yet taller, until you really reach a limit where it becomes an impulse, a unit impulse function, which is really a limit. So this is where sigma becomes smaller, smaller, and smaller. So then this happens, then we call it an impulse, a unit impulse function. So that's all you need to know for now. Just remember that then you take a Laplace transform of this function, it is 1. And then you take a Laplace transform of a unit step function. It is exponent over s. Right? Then another rather cumbersome expression is the Laplace transform of an exponential times the power, which is this. And a few comments about the Heaviside step function. So this is a very useful function, commonly appearing in signal processing and engineering. So if you haven't seen this before, definitely remember this. So it becomes 1 after t is greater or equal to a, and 0 otherwise before. And it's very, very handy to understand sudden turns on and offs of signals. So pay attention to the definition and remember its Laplace transform. So this is the table of Laplace transform. You can find it on Blackboard. So please always keep it at hand, look at it periodically, and whenever you can, try to use Laplace transform by table to calculate Laplace transforms. That's for now.